Hello everyone. Now we will continue our discussion about reservoir simulation, especially for IMPES solution. Now we will continue the section, and it's about discretization of flow equations, focusing on the upstream mobility term, which is the left side of the equation. Okay, so you can read it with me. Because of the strong saturation dependencies of the two-phase mobility terms, the solution of the equations will be much more influenced by the evaluation of this term than in the case of one-phase flow. Okay, so in two-phase system, the mobility term has strong dependencies on saturation. Okay, previously we have this equation for the mobility, all right? And you know that the relative permeability is a function of water saturation, okay? So yeah, in two-phase system, now our mobility term is strongly dependent on the water saturation. All right, recalling the Buckley-Lefferts solution to the problem of displacing oil by water in a one-dimensional system, we will use it to illustrate the effect of mobility on the saturation solution. So if we have our system here, and here we have rock containing oil, and then we want to displace the oil. We want to push the oil using water at flow rate of QW. All right, so here we have the rock, the core containing oil, and we want to displace, kita ingin mendorong the oil using water. Now we want to plot the saturation profile. On vertical axis, we have water saturation. This is Buckley-Lefferts method. And on the horizontal axis, we have X, the length of the rock. All right, and we have the minimum water saturation, which is irreducible water saturation. And this one is 1 minus residual water saturation. I mean, irreducible water saturation. 1 minus irreducible water saturation. This one is irreducible water saturation, or you can also call it Connaught water saturation. All right, and here we have oil. Okay, so here we have waterfront. So in front of the waterfront, we have high saturation of oil, and the saturation of water is at here, the irreducible water saturation. That's for in front of the waterfront. Okay, behind the waterfront, di belakang garis ini, behind the waterfront, we will have here, increasing water saturation profile. Okay. All right. Here, for negligible capillary pressure, the water will move through the porous medium as a discontinuous front, as illustrated in the figure. Okay, so it's like discontinuous front. You can see by looking at this front. It's discontinuous. In front of the front, we have high oil saturation, and the water is at irreducible water saturation. Okay, in simulating the process using a discrete grid block system, we will find that the results are very much dependent upon the way the mobility term is approximated. Two cases will be considered using flow of oil between blocks I and I plus 1. Okay, so we will have example. So first, we have upstream selection. So the mobility of oil at I plus half equals to mobility of oil at I. And then number 2, weighted average selection. So the mobility of oil at I plus half calculated like using this equation. Okay, so we will consider two cases. Now we want to discretize our porous media. We want to discretize our rock, our core. Okay, the results of these two selections on the saturation profiles calculated by the simulator will be illustrated. So let's say if I discretize my rock like this, so I have n equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and I have exact solution using Buckley-Leverett method here. Okay, this black line, and I have average method, this dashed line, and the last one I have upstream solution. So upstream selection here. The solution is, you can look at this dashed line. This is the solution. Okay, so I think you can see that the upstream solution is better because the solution is closer to the exact solution. All right. The average solution is actually good, but it is not close enough to this solution, the exact solution. Okay. So again, we displace the oil using water and we create the saturation profile. Okay, we generate the saturation profile first, exact method using analytical method, Buckley-Leverett method, and then we also use numerical method. We use upstream selection, and the second one is weighted average selection. And you can see that upstream method gives better solution because it's closer to the exact solution. All right, so you can again read it with me. Of course, the deviation from the exact solution depends on the grid block sizes that is used, of course. Yeah, if you increase the number of grid blocks, of course, the solution, the numerical solution will be closer to the exact solution. For the downstream selection, water saturation behind the front may even become negative for a large block. I mean, the smaller the grid block, the better, the more accurate the solution will be. For very small grid blocks, the differences between the solutions, you can see, may become negligible. Okay, so if you discretize the rock, discretize the porous medium into very small grid blocks, you will have huge number of grid blocks, then you will have solution that is very good, close to the analytical or exact solution. Since the same amount of water has been injected in the three cases, the areas under the three curves must be equal, and only the location of the fluid front has been shifted, as well as the magnitude of the water saturation at the fluid front. Okay, so the area under the curve must be the same for these three methods, yeah, because here same amount of water has been injected. The difference will be on the location of the fluid front. For exact solution, the location of fluid front is here, and for the upstream solution, here the water front, whereas for the average, the water saturation, I mean the water front will be here. Okay. The physical explanation of the differences, and in particular for the case of weighted average mobility selection, is that the flow rate of oil out of any grid block depends primarily on the relative permeability to oil in that grid block. Okay, this is important. especially for weighted average mobility selection, the flow rate of oil out of any grid block depends primarily on the relative permeability to oil in that grid block. Okay, so you have one grid block here and you have the flow of water. The flow of water going out of this grid block, the flow of water going out of this grid block depends primarily on the relative permeability to oil in that grid block. Okay, so relative permeability is very, very important. Okay, in particular for flow between blocks I and I+1, the relative permeability of block I will determine when the flow is to stop. It as when the block has reached residual oil saturation. If the mobility selection is the weighted average, the block I may actually have reached residual oil saturation, while the mobility of block I+1 still is greater than 0. Okay, so this can be complicated. Okay, for flow between blocks I and I+1, the relative permeability of block I will determine when the flow is to stop. Okay, the flow will be stopped when the block has reached residual oil saturation. If the mobility selection is the weighted average, the block I may actually have reached residual oil saturation, while the mobility of block I+1 is still greater than 0. Okay, therefore, flow out of block I will not stop before the relative permeability of block I+1 also has become 0. Okay, so let's say we have block I here and block I+1. Okay, flow out of block I here, flow out of block I. Okay, flow here will not stop before the relative permeability of block I+1 here also has become 0. So if the relative permeability of block I and I+1 have become 0, then the flow will stop. All right. Again, for small grid block sizes, the error involved may be small, but for blocks of practical sizes, it can become significant problem. All right. And then we continue. Therefore, in reservoir simulation, upstream mobilities are normally used. And using the plus direction example for flow of oil and water system, we will have this. Okay. So by this explanation, the conclusion is that we want to use upstream method, upstream selection here, where the mobility of oil at block I plus half equals to mobility of oil at I. Okay, we prefer upstream mobility. Okay, upstream selection of mobility here, mobility of oil at grid block I plus half can be explained like this. So it will be mobility of oil at I+1 if the pressure of oil at I+1 equals to or greater than pressure of oil at I. And then this one. And for the water, it's like this. So we have oil and water flow system. So again, mobility of water at grid I plus half, okay, it will be equal to the mobility of water at I+1 if the water pressure at I+1 equals to or greater than water pressure at I, but it will be equal to mobility of water at I if the pressure of water at I+1 is smaller than pressure of water at I. Okay, so you can follow this in the simulation. This will be applied. Okay. Now from left side of the equation, we will go to the right side of the term. Okay, I want to show you again the flow equation that we have in this slide. Okay, so we have left hand side and right hand side here. Okay, of the flow equation. All right, we continue to the right side. The right hand side of the oil equation may be expanded as follows. So allow me to go back first. The right hand side is this. ddt of porosity, oil saturation divided by oil formation volume factor for oil, and for water, it's like this. Okay, so if we want to expand this, okay, the first one is the porosity divided by BO, assume constant. It's like this. So we have DSO dt, and then plus saturation of oil constant. It will move out. So we have SO here, d dt of porosity divided by oil formation volume factor. So that's how we expand the right-hand side. And since the derivative part of the second term is identical to the right-hand side of the one-phase equation, we may write an approximation for this directly. So here, the second term, ddt of pressure divided by BO at I, okay, it's identical to the right-hand side of the one-phase equation. Okay, so approximately porosity at I divided by dt multiplied by this term multiplied by the pressure difference. Okay, for the first term, we will replace oil saturation by water saturation. Okay, we will replace oil saturation by water saturation so that dSW dt equals to minus dSO dt. Okay, for the first term here, this is the first term. Then we may use a standard backward approximation of time derivative. Okay, so porosity BO dSO dt, this term. Okay, approximation minus porosity I divided by BOI delta TI and the change in water saturation. The complete difference form of the right-hand side of the oil equation may thus be written as, so I want to rewrite this one with approximation. Now here, this is the equation. The capacity multiplied by the pressure change, and then this is for water multiplied by the saturation change. And this is for the term, this one, and for the CSWOI here. This form comes from, actually from here and from here. So we just want to make a good shape of equation to be applied in reservoir simulation, in our reservoir simulation using IMPES method. Okay. So for the water equation, a similar expansion is carried out. So first we want to expand the porosity BW go out multiplied by dSW dt, and then water saturation goes out, ddt of porosity per BW, and then the second term in this expression, this one is expanded, okay, d dPW of pressure BW dPW dt, and then we get this. You can just follow the logic, you can just follow the equation. Since capillary pressure is a function of water saturation only, okay, so PC is a function of water saturation only, we may write here the derivative of capillary pressure for oil water system with respect to time can be written like this. Using the one-phase terms and standard difference approximation for the derivatives, the right side of the water equation becomes like this. Okay. All right, so here we have the right-hand side of the term and the CPOW here and CSWW here. So you get the right-hand side of the flow equation. Okay, so the discrete forms of the oil and water equation may now be written as this one. It looks great. Now the flow equation that we have is shaped like this. Don't forget T is the transmissibility, C is capacity. Okay. This is for oil and this is for water. Now we don't have any differential form. We just have plus and multiply and minus. So now it's easier for the computer to use this computation, this calculation. Okay. Complete definitions of the terms in the equation are given below. So for transmissibility of X, oil transmissibility at X direction at grid block I plus half is here. Don't forget lambda is the mobility. And this is for the transmissibility X at I minus half for oil on the left and for water on the right. That's for the transmissibility. It's not about right-hand side again, okay? It's just for discretization of flow equation. So you can neglect this one. Okay, so I have erased that. Continue. All right, we have the lambda here. So lambda of oil is relative permeability of oil divided by oil viscosity and oil formation volume factor. And the upstream mobilities are selected as follows. Okay, so again, we use upstream mobilities. And the right side of the equation, we have CPOQ, we have, CPO CSWOI, CPOWI, CSWWI. And you can see on the right side, this is actually the true form of this term. CSWOI is this one. CPOWI is this one. All right. The three derivative terms appearing in the expression above are this one, the 1 per BO, DPO, the or DDP of I per BW, and the derivative of capillary pressure with respect to water saturation. They are all computed numerically for each time step based on the respective PVT and capillary pressure input tables inside the model. So we have PVT data, we have capillary pressure data, we input that in our reservoir simulation in the model. So these three differential forms will be computed numerically for each time step based on the given data. All right, here we have one differential here, one differential here, and one differential there. Don't worry, we will compute using numerical method. All right, so that's for the flow equation. And of course, to solve the flow equation, we need boundary conditions.